Uh, maybe it's our. Oh, okay. Yeah, it's great. So, very happy to have Michael DeMarco here. Michael is from Brookhaven National Laboratory, and he graduated from MIT, and he's doing this beautiful work for C2QA, which he's going to talk about. Michael,
that's great.
pleasure.
So thank you all for coming. This is a big work that's come out 2 days ago on the archive, and it's a white paper coming out of what's called the Co-Design Center for Quantum Advantage. If you're not familiar with this, it's one of the DOE centers that the Department of Energy put together to advance quantum computing. So we have about 25 universities. We used almost all of them in this project, or actually we just used 14. And it's a massive team that we built to do this analysis. I'll only get to tell you about some of their contributions today because there's only roughly 45 minutes here. And my background is a physicist. I was a field theorist for a long time. I'm actually going to be speaking today in a very computer sciencey language. So does anybody have any experience with like computer networks or network architectures here? Cool. I didn't either. So okay. We'll get to share a little bit of this idea and sort of what we are thinking about quantum computing are sort of interested in and stealing from classical computing architecture. And it seems like we have maybe a third of us are familiar with quantum computing ideas. So I'll try to explain sort of a lot of what we're trying to build here. And today it's kind of about multinode quantum computing. So let me start by drilling down deep on what I actually mean by that. So in quantum computing, and Simeon, I won't be able to see any messages from Zoom, so let me know if you can come up. Cool. Wonderful. And also, if there's any questions here, it's a small enough group, just go ahead and ask it. We can make it a seminar for you guys. You'll hear this a lot in quantum computing, sort of multinode or modular or distributed ideas. And they're all the same basic idea, which is rather than making a giant quantum system, which is very challenging, let's make a bunch of small quantum systems and network them together. And the fabrication challenges we've seen there are the same reason, like this laptop I'm talking or speaking off of doesn't have one giant CPU. It has a bunch of little CPUs which are connected together. So here's some old pictures. This is from like 2006. So some of you early trapped ions people. If you've heard of this billion-dollar quantum computing startup IonQ, this is from their founder and team. A bunch of those people wrote a really nice Scientific American on this, and it's actually starting to become reality. So this is IBM's quantum roadmap. So in a few years, they're actually starting to network their chips together with quantum links to make a sort of genuine quantum network within one of their devices. And if you know anything about quantum, you'll know that there's a bunch of different people trying to build quantum computers. And so far, we haven't gotten there. And they're all fighting each other for who's going to actually build them. Right? Is it ions? Is it neutral atoms? Is it superconducting devices? I work with superconducting devices, and I'm actually going to spend all of today sort of hyper-focused on one type of this technology, mostly because that's the level that we need to be at to actually predict where hardware will go. So here we actually have one of these here. It's a dilution refrigerator. I love these things. I don't work on them, which is why I like them. We have to do all of our stuff very, very cold. So a superconducting chip needs to be about 10 millikelvin, which is just an insanely low temperature, even for winter in Iowa. We'll have one of these big refrigerators. They're about as tall as I am, about this big around. And up here, the temperature will be something like 60 Kelvin, and by down here, it'll be 10 millikelvin. And it's extremely expensive to buy one of the things. They're about $500,000. And if I want to start thinking about this idea of big quantum systems networked together, I run into a problem, which is if I can't just put a bunch of chips down here, because I run out of space and I run out of cooling power. And everybody started to look at this, and you'll see this again. Well, why don't we just have multiple refrigerators? So I'll put one chip over here, one chip over here, and I'll network them together, with some quantum links. That's a wonderful way to go, and this is something which is not explicitly in the roadmaps, but frequently discussed among the major companies that are doing superconducting quantum computing. If this is how we're going to scale to really large sizes. There's a trick with that though, which is if I want to go between two refrigerators, I can either try to make that cold all the way at a few degrees Kelvin, which is very challenging, or I can have a warm room temperature link. But if I do that, I have to change the way my information is encoded. In particular, superconducting devices, they operate in microwave regimes, and you can't put a microwave photon down a room temperature wire because there's a bunch of microwave photons just thermally populated in the wire. It's why all of our telecoms happen around roughly optical or near IR wavelengths. So no, cool. Much something like 1500 nanometers, 1200 nanometers, not 5 gigahertz, which is where our superconducting hardware operates. So if I want to be able to network these fridges together, I have to convert my microwave photons to optical. My information is encoded in them to optical. And that's called transduction. And that's a nonlinear process. Now, the way I like to think about it is the reason any of us have careers is that physics is largely linear, right? The nonlinearities are perturbation. Otherwise, we could never make sense of any of this. Newton would have never written down F equals ma, and this never would have happened. The bad news is it means the transduction is just obscenely hard to do. We have a bunch of experimentalists working on this. We have a really boss one in the center, is Tom Tang, and an amazing group. And he will tell us that someday the theory should be ready to lose 30 decibels of signal. That means that's just a colossal signal loss. And all the operations there are somewhere between 100 times and 1,000 times noisier and slower than they are within a fridge. And you can kind of see the question I'm lining up here. How are we ever going to surmount this? I just want to meditate on this. Like 30 dB of loss is sort of like 1 in 1,000 photons makes it through. So we fire 1,000 photons, 999 of them die. And here we are, we're only getting 1 out of every 1,000. Somehow we're still going to do it anyways. So that's the attitude we need to have here to make this work. But okay, what do I mean here from a systems analysis perspective? I want to take this question: how are we ever going to surmount this and make it tangible? So this link performance, this internode link between those two refrigerators is a serious problem. And not only is it going to be noisy and slow, but it's going to have to compete with something with local gates. So I could just stay within one refrigerator. That would be better, it seems like. And I can do something called classical circuit cutting. And that's a new technique that's come out in the past few years, where instead of doing a quantum operation between these two fridges, I can do a bunch of measurements and execute the circuit a bunch of times. And so if I do that, I can actually reconstruct the quantity. And it sounds like cheating, it comes at a price. So what I really want to understand here is, what is this trade-off like between internode gates, local gates, and circuit cutting, given the hardware on these internode gates in a multi-node quantum system? So just to really focus on that right here, and I want to emphasize this: given current planned hardware, what are we going to do here in terms of internode gates, and how does that trade off with local gates or circuit cutting? So I will tell you all about how these multi-node systems are designed and how to get these answers. But does that kind of make sense to everybody? This is a good point. If I haven't set up the question in a way that feels familiar to you yet, this would be a wonderful time for a question. All right. So that's an overview of multi-node quantum computing. Let me dig down into what I mean by a multi-node quantum computer and the components in it. So this internode gate, the way we're going to execute it, I mean, if you have 999 of your photons dying and sending them down this line, you want to only use them when they actually make it through. So we're going to use a thing called heralded entanglement generation. Everybody here knows what a bell pair is? Is this familiar for quantum mechanics? I know if you're like a hardcore astrophysicist in classical, that might not be a thing. Cool, perfect. I'm going to distribute some entanglement between my refrigerators, and instead of immediately trying my computation, I'm going to have some signal that tells me when it's actually successful. Okay? That signal is noisy and often wrong, so there will still be noise in there. Now, so I'm going to take that heralded entangled pair, and I'm going to do what's called entanglement distillation, which is a way of taking a bunch of noisy entangled pairs and getting a handful of less noisy. So you're sort of distilling the entanglement, just like you would liquor. And lastly, I'm going to use that entanglement then finally do remote data execution. And that's just like really complex process. Like each of these has a lot of papers written on it. And we have to somehow string all of them together to get some idea of system performance. And it gets even a little bit trickier here. So like if I just try to simulate all of this in one, I end up paying for every internode link about 20 qubits worth of simulation, which is a Hilbert space of 2 to the 20, which is tough to simulate, but not undoable. But this is like still part of a larger computer. So if I have just a 10 qubit computer with one internode link, I'm looking at simulating 30 qubits, which is about 16 times bigger than the biggest density matrix simulations that have ever been done. So clearly, like, that's not the direction I want to go. What we will see today was mostly done on laptops. Some of it was done with HPC, but could have been done on by laptops. We were just speeding it up because we had an amazing HPC team. And for all of this, I need to understand how the system optimizes over these 3 resources. And lastly, sort of a very tricky part here is that all the hardware is still in flux, right? I'm going to focus on one specific hardware model, but I better build the analysis in a way that when somebody comes by and says, actually, forget what we were doing before, this is how we're going to do microwave transduction. Or forget what we were doing before, here's a dedicated circuit for entanglement distillation. I want to build my analysis so that it survives changes like that. We can kind of modularly pluck in components and put them out. Now, the hard part about quantum computing is this terrible noise, that our hardware is like always flipping from 0 to 1 when we don't want it to. It's decohering. The nice part about quantum computing is that classical computing has existed for a century and come up with some really cool stuff that we get to steal. So most of the talks I give, there's some point I set up a hard problem, and I'm like, I'm going to steal a bunch of moral lessons from classical computing architecture. This is that point in this talk. And if you ever study the internet, it's actually kind of amazing. The way that the network is set up is in a series of layers. So each layer is responsible for some portion of the internet. It only communicates to the layers sort of above it, below it, in a stack. And there's a very specified way to communicate. So for example, your computer operating system doesn't have to worry about whether it's plugged in via Ethernet, not that anybody has Ethernet ports anymore, but okay, or using Wi-Fi, or communicating via Bluetooth to learn how to send a file. It just sends the file. And then the network itself worries about translating that to the particular language of the network. That's an example of a layer architecture. We're going to steal that idea. We won't be able to use really any of the technical details of internet layer architectures. But the basic idea of separating your system and connecting these layers together can be really important. And it was a huge way to that big complexity we were facing is a way to sort of segment that down and overcome these exponential growth of complexity. So for us, what we want to do is, remember, we're going to generate entanglement. We're going to distill that entanglement, and then we're going to execute remote gates. And then finally, at the top, I have a computer. And I want to do this layer by layer. So each layer doesn't care about the things before. I have a simulation just of making physical layer qubits, so just producing entanglement. I don't worry about distilling. When I start to distill it, I don't care about how it's produced. It's just an input. Okay. So instead of these two together cost about 20 qubits. Instead of doing that, I have a bunch of individual 2-qubit simulations. Okay, maybe 4 or 6 of them, and then something like 16 to 18 simulations here of individual 4-qubit models. So this is a lot more efficient because it allows you to cut down that exponential growth. And when I do this, finally at the top, as a computer, I don't care about all the complexity that goes into internet communication. I just care about whether an operation happened and how noisy it was. So I go from a 20-qubit gate to a 2-qubit gate. And that really cuts down on my complexity. And just to give a quick idea, I don't want to drag too much through the details here on how we do this. So let's say we want to generate this entanglement. That was the very lowest layer. And like I said, with losing 999 out of 1,000, we better use a heralded scheme. So it gives us a signal that it succeeds. The way I do it is let's say here's my first bridge and my second bridge. And I have a qubit, this is 3 lines, and I have a wire coming out of them. I can actually entangle a photon between, or entangle the qubit and the wire by splitting a photon between them. And do the same here. And at some point, I convert these wires from microwave to optical, this into a converter. They come out and they'll actually interfere, and I'll get clicks on these detectors. And when the clicks fire, my qubits end up in there. And this is something called a Hongo-Mandel protocol. There's some magic in it. Frankly, the magic here is that you'll get a click in neither detector or both detectors, never just one. It's one of the lovely things about quantum mechanics. But there's also something cool here, which is I start by entangling the qubit with the wire, and I can change the strength of this entanglement. The stronger it is, the more likely I am to actually produce a pair. Okay, so the faster I get entanglement produced, but the more susceptible I am to noise. And that's a trade-off that we're going to see a lot. You can do things more quickly and pick up more noise in a quantum system. And the two things that kill quantum systems are noise and noise. So you might think more quickly is good, but actually a different kind of noise is also attacking you all the time within the nodes. And so you want to be fast too. So we'll have to learn how to trade off between those. Okay, now I want to do entanglement distillation, and just to sort of quickly go through this, the idea is entanglement distillation, you can start with two noisy pairs and end up with one less noisy pair. That's the sort of simplest version of it. And there's many more complicated versions I don't want to get into. But basically the idea is, so here, every time I do a round, so 0, 1, 2, 4, 6, I lose half my pairs, but my infidelity, so the error, goes down. So fewer errors, but I'm blowing through a lot of pairs, which will end up slowing down my computation. And that's that same theme I want to introduce. We got less error, but a slower execution. And that's, again, this trade-off that we'll see just again and again. Finally, I just want to remark on this. There are very well-known procedures. We're not innovative on this end of how to take entanglement and use it to execute operations at a distance. We probably all learned quantum teleportation in some class. Did everybody see that at some point? So that's basically an operation, is a swap gate between here and there. You can use that to do all sorts of gates, and in basically the same way. And what we're going to do is stitch all these together. So I can take each of those layers and start to answer one of my very first questions, which is, what is the performance available of internode gates? I didn't want to know what this means for system. I'll get to that in a second. Just what performance can you do? Okay. And so using that model, I can stack those simulations together and try to ask, hey, what's the error rate? So that's the infidelity here. Down is good. And the lead gate time, which is here, so to the left is good, that I can achieve. And the first thing I might do, let's start in this column here, is just use the raw entangled pairs that we generate. Those are going to be the fastest possible, but they're going to have a lot of noise. And that's this black line here. So the red is just to kind of guide the eye. But you can see this black line based on that tunable parameter of how entangled my qubit and wire were. I can lower my infidelity at the cost of increasing the time. So you can see there's a little curve. What's more interesting, though, is as you go to higher and higher rounds, this curve moves to the right and down. So I am increasing my link gate time. That's bad, but I'm decreasing my infidelity. That's good. This is a sort of trade-off you pay no matter what you do. And in that, we sort of get this nice figure of, when I showed this around, people first said it was a dog, right? Because it's like a snout and ears, so it started to be called the Snoopy curve. And you can see that as we do more and more distillation, the error rate goes down. I now have this sort of interesting trade-off between a few different parameters. So the more distillation I do, I actually need to change how I'm doing my entanglement generation. So here I want to be at the far end of this curve. Here I'd actually like to be in the middle. And definitely by here, I need to be right in the middle. So there's several things that have to know how each other are working here. Particularly the entanglement generation needs to know how the distillation is operated, which is sort of a cool thing in the architecture. And finally, if I do too many rounds of distillation, other errors start to build up. And so you just give up. Snoopy's going to lose his tail. He's like a schnauzer or something. And here's one of the many jokes I've lined up. But I asked this guy to go and draw me a a dog. This is from DALL-E 2. And it turns out it's better. So here's a depressed looking Snoopy wondering if he's going to have a job now that DALL-E can just draw dogs. So those are my multi-node quantum computing components. What I want to talk us through now is how to think about a quantum computer as a system, as this really complex interconnected device, and think about all of these layers together. This is a crash course in computer architecture for physicists. So thank you for coming along. So remember, I had this layer structure, and what I want to do now, we've basically gone through these three and then learned how to stack them together and understand internodes. What I want to do now is understand what these internode gates mean for actual quantum computation. What kind of performance might I expect, and what can we get to? So for that, I'm going to introduce three different models. They're going to be called a gate algorithm performance model, a quantum roofline model, and a quantum classical performance analysis. So we'll see these in a few different ways. And the picture I want to use just to sort of talk us through, I don't want to, I suppose it's too much of the process, but I think it would be remiss not to share how all of these people ended up contributing to this paper. Each of these layers, like I mentioned before, is sort of a research project unto its own. So what we did was get the leading groups for each of these to do their own simulations and then connect them together. So here, Yale was our big physical layer. They're also doing the entanglement generation themselves. So they actually have a giant dilution refrigerator doing this. It's really a heroic experiment. And they lent us a bunch of their people to do all the simulations for this. The Princeton team headed out, how do you actually catch these photons that come out of the Yale team's work and move them into a quantum device. And once they're there, this distillation process was headed by Virginia Tech. Us at MIT did a lot of the data layer, as well as built this physical layer in BNL. And Pacific Northwest National Lab, the one who built the data pipeline to connect all of these together and did a lot of the upper layer simulations along with IBM. So these are just the leads of the teams. They're all spread out over universities. I'll get to tell a little bit more later. But I just want to give a sort of picture of what this sort of analysis requires to bring all of these people together. So let me focus now. We've seen now sort of what is the achievable performance of internode gates. The second question I need to answer is, what does this mean for system performance? So what I'm going to do here is I'm going to take that Snoopy plot, and I'm going to put it on top of, so Snoopy's already lost his tail, unfortunately, but I'm going to put it on top of a success region plot. So what this is I have a certain benchmark, and it's called quantum volume. Now, it's put forward a lot by IBM. It's roughly a measure of the effective Hilbert space that your system can traverse before noise kills it. So it's, it's some 2 to the number. And I'm going to imagine this very simple, the dumbest, most straightforward multi-node architecture I could come up with. So 2 5-qubit nodes with 1 internode link. Now, if all of this was perfect, the quantum volume of this would be 2 to the 10. There's 10 qubits. If there was no internode link, it'd be 2 to the 5. And I want to know, how much does this buy me? Okay? So this is that same plot. Here's the error, and here's the time. Here's Snoopy, and here are my success regions. So you can see that Snoopy's out in the cold. He is nowhere near even being able to modestly outperform a single node system. This is, I think really characterizing how extremely difficult these experiments are. But it's not all bad news. In fact, it turns out that thinking of multi-node systems, and this is what we're starting to learn, there are more efficient things that you can do, and pretty exciting ones. If I then look at a bunch of other algorithms, these are sort of classic benchmarks that we use for quantum systems. The most important one here is actually this, the easiest, the GHZ state. The idea here is I want to put my qubits in a superposition of 0, 0, 0, 0, 0, 0, 0, plus 1, 1, 1, 1, 1, 1, 1. And that might seem like so simple. It turns out that that's extremely important for something called distributed phase estimation that we won't get to in the talk, but if there's curiosity about it later, it's a pretty powerful algorithm. And even for more complicated things, you can kind of solve some extreme numerical problems. We can't get down here. This will be quantum field theory to everybody. On this plot, it's actually the quantum Fourier transform. So That's the really important one. Down here is where you start to get into small cryptographic applications, which is one of the key directions that quantum computing wants to go. So we can get some of these important algorithms that are important for quantum simulation, like GHC. These more cryptographic and computational applications, we're not there yet. So with that, I think we've now seen literally what was the performance of the internet gates and what did it mean for system performance. Breaking down that first question I asked, I need to go from internode gates to local gates and understand this trade-off. And to do that, I'm going to use something called a roofline model. This is another idea I'm more or less stealing from classical computing, though. I think it's kind of like I think lots of branches of physics steal from each other. In stealing from classical computing, you actually can't take too much of the actual framework. You just have to learn the moral lessons. This is another one of those. But the moral lesson it's taught us is that there's an optimal way that hardware likes to be operated, and there's an optimal way that programs like to be run. And your life is good if those are the same, and it's painful if it's not. So the right way to think about how a program likes to be run, let's start there. It's called the computation communication ratio. And it's literally, I have some quantum program, I want to execute it, and I tabulate how many local gates does it involve and how many internode gates does it involve. And I divide it. And I can then figure out what my hardware would like to do. And the right thing to do is it's a preferred or machine CCR. And what I do there is I figure out the amount of time it takes an internode gate to run and divide it by the amount of time a local gate takes to run. And my life is good if these are equal. A nice way to see that is if my internode gates are very slow, they take a long time, then I would like a lot of local gates and not so many internode gates. And we can actually plot this, and this is where the roofline story comes in. So here, what I have is gates per unit time on the y-axis, and this CCR on the x-axis. And this is sort of like how much computation I can do. So I can go below this line. And to the right of this line is how much communication I can do. So anywhere in here is fair game. The balance point where these two are equal is right here. So I would like to be as close to here as I can. Quantum compilers are pretty inefficient. This is pretty far away from that point. This is a logarithmic scale. So we need to be pushing towards this point. And even cooler, what this lets me do is understand how the machine changes as I do something like distillation. So if you remember in that Snoopy plot, we had all these black lines that are moving to the right. So here's the first three and what they do to this model. So as I distill more and more, it takes longer and longer to do an internode computation. So my bandwidth goes down and my communication bound gets more stringent, right? So I can only work under this line and I'm having to move to the right. And now, in fact, my balance point changes because as internode gate time goes up, this ideal CCR goes up. So this moves to the right. This is where I work. And so this gives me a really nice way of understanding how I should trade off the internode and local computation. In fact, let me go back just a slide. If I had a choice to not use an internode gate and just do local computation for 10 gates, should I take it? It's like you want to establish the exchange rate, and this MCCR is like the preferred exchange rate. It's like the LIBOR rate. It's like the one that they got caught rigging a few years ago. I don't remember. It was like $1 trillion scandal. This is like that. And as my hardware performance, my network operation changes, I do more distillation, that exchange rate, ideal exchange rate changes. And now I have a nice tool to guide my compiler on how it should be optimizing the systems. So this is the quantum roofline model. Let me then zoom in one more time. So we saw this connection. Now I want to do this last connection. This is this magical thing called circuit cutting, which like the point of quantum is you need quantum to do it, right? That's kind of, we want to use these computers to solve problems we couldn't do any other way classically. Circuit cutting kind of feels like cheating with it. It's like, don't have a quantum gate, just do it classically. So what's the price there? And there is indeed a big one. The way a circuit cutting gate works is it says instead of actually running the quantum leap, all they have to do is do this circuit a bunch of times and do a bunch of measurements on these two qubits, and I can reconstruct what the gate would do. And in fact, what you need to do is 4 measurements for every gate you cut. And it's exponential. So there is a price. 4 to the k is actually brutal scaling, considering that we might want 50 internode gates. So that's this plot here, the number of internode gates and the number of executions required. This is 4 to the k. Okay. Now I'd like to compare that to actually having a quantum gate. And the way to do that is actually, I need to compare apples to apples, so I'm allowing multiple executions. It's used something called error mitigation. This was also heavily developed by IBM. There I also use multiple circuit executions. And the idea there is sort of like, if I do this circuit a bunch of times, the errors will average out. So for internode gates, it's again some scaling, gamma to the k. So 4 to the k of gamma to the k, but gamma is way smaller. It's like 1.02 to 1.52. So this is an exponential advantage. And I just want to compare how they play out given the noise of these quantum systems. Whereas, so we saw in some cases we might have 10% noise. So that's a fidelity of 0.9 in the lingo. This is still colossally better, like 10 to the 10, 10 to 15 times better than circuit cutting. Even given how noisy these quantum gate links are, they outperform the classical links by a factor of up to 10 to the 15. That's colossal. And it gets better as we do more distillation, as we get better and better quantum gates, this curve goes down and this gap grows. And just as an example here, remember we had this quantum volume that sort of briefly flashed on the screen, and it was 2 to the 5 to 2 to the 10. So for 2 to the 8, I have, I think, 42 internode gates. This is clearly not something, I'm not going to be doing 10 to the 25 circuit executions. That will never happen. So even just to really get the system, this little imaginary 2-node systems where I want it to be, you clearly need to be using quantum gates here and not classical ones. Okay. So just to summarize, we saw that these internode gates are extremely noisier and slow. But one, we can get some simple algorithms to run that are critical for early stage quantum algorithms. And two, even given how noisy and slow they are, they sure beat the pants off of circuit cutting and in many cases local gates. So I think what I wanted to present here is a sober view of this very promising realm of quantum development and where it is now. What I'd like to do in the last bit of this is talk about where we want it to go and where we need it to go to actually produce viable quantum computers. So that's going to be the roadmap to multi-node quantum computing. And the question I want to ask you is, okay, we saw this thing barely outperforms a single node. It really doesn't at all in quantum volumes. So what do I need to do that? So they outperform nodes with the multi-node system. And if people are proposing hardware and software advances, how can I see what makes sense? I hope so far, if there's something I want to instill, it's sort of a warning about the complexities of the systems. You have all these trade-offs and they go in different directions and it's not clear how to maneuver through them to build a quantum system that actually delivers. And that's what the stack architecture, again, I have to keep coming back to, helps us do because it compartmentalizes the complexity and allows us to understand each layer. And we're going to need to get improvements at every layer. So we want to see better 2-node gate execution with sort of noise-aware circuit design. We're going to see both hardware and software advances to entanglement distillation. And we'll want to see both hardware and a little bit software advances with the way it interacts with distillation at the physical layer, the generation of entanglement. And I can use these same pictures to start to understand that story. So just as a brief example, the yellow groups have a lot of improvements that are sort of in progress in how they generate entanglement between two refrigerators. And we could take their simulations and plug them in and say, okay, this is where we are now. Here's where Snoopy started. This is where it goes next. So clearly down to the success region. And opening up, so that would be opening up my bandwidth. So I have a much more space to work with here. or widening this gap to almost infinity between the classical and the quantum gates. And it kind of goes on. We talk about multiplexing, which sort of improves my rates. Again, going down the stack. A big game changer here would be totally changing the way we do transduction and directly coupling superconducting qubits to ions, which would take us all the way down here. And this is just the physical layer. I can sort of flash through these. We can look at just carefully understanding the way that we do entanglement distillation and how that interacts with a particular noise in the system. We can look at quantum memory, which a 1 millisecond quantum memory exists. In fact, almost 3 millisecond quantum memory is now being made at Yale. It's extremely exciting. Reading in and out of it is hard though. If we had ions, this would be a 2 millisecond or even 1 second quantum memory, which would be a complete game changer for us. Being able to store superconducting information for a second when our gate times are 100 nanoseconds is a lifetime. That would be really, really neat. And we can look at the same stories in software and efficient compiling new distributed algorithms. This is where we kind of ended up with 33 authors, right? We had about 13 people doing the original analysis, and it came time to build a coherent vision to how do we get towards distributed quantum computing. We realized we had so many people to join us. In fact, one of our authors is here, Youngshin, came over from Ames. Youngshin articulated, particularly here, in these new distributed algorithms, where should we be looking in material science and condensed matter simulations towards this direction. So this is sort of the idea, and a lot of what we're trying to do here is both iterating and improving on current architectures, but trying to find these game changers like that ion coupling. We're probably going to get one of those, which is great because we only need one. We have the iterated improvements and one game changer. We'll be where we need to be. So now that's what we're going to distribute out quantum computing. I'm going to step back from my very intense focus on a single platform here, just to kind of summarize. We saw that our internode gates are going to be 10 to 100 times noisier and slower than local gates. That's a lot better than the 100 to 1,000 that we might have been naively expecting. But even given that, we will see some quantum computation above the performance of monolithic systems before too long. Those trade-offs with local and circuit cutting gates mean that despite how noisy this is, it is worth building it. And we'll want to see these sort of steady progress in our current technology and game changers. And so just to offer sort of a last thought here and close out, I have been maniacally focused on superconducting systems. Partially because that's what we have in the center, partially because to do this level of analysis, you have to just pick one piece of hardware. This is a 25-page paper with 33 authors. Something like this should be done again for each of the different platforms. We should have the same detail of understanding with even superconducting systems with microwave interconnects. I have my fridges, I can build a bridge. It's extremely expensive, but maybe that's what we should be doing. With ions, they can be shuttled around, or you can use optical connections between them. And the same goes for neutral atoms. So there's a lot of really interesting directions here. And it sort of highlights, I think, my favorite thing about distributed quantum computing. Because again, this is one of those places where we should learn from classical computing. If I had a system with superconducting nodes and trapped ion nodes and neutral atom nodes, they would all have different trade-offs. The superconducting systems would be extremely fast. Gates 100 nanoseconds. That's super, super quick. But they're kind of noisy. You really don't want to be storing information there. But my trapped ions, they have seconds. They have like 10-second lifetimes. Or neutral atoms too, right? That's colossal. So trapped ions are going to be more like a second. Neutral atoms are going to be more like 10 seconds. That is a long, long time in quantum information. And now I start to look at, like, maybe I have compute nodes and memory nodes. And maybe that's actually the architecture that made early computer networks work. That shared distributed memory was extremely important in the AOS and connection machine architectures. And that's sort of what we want to be able to enable here. Not just big systems of one monolithic kind of platform, but start to look at distributed systems where we have a heterogeneous architecture at the highest levels with ions forming memories, superconducting forming compute nodes, and on and on. That's, I think, the power of quantum computing and a direction towards really getting towards these scalable systems. I don't want to in any way underemphasize the difficulties between here and there. That's why we had this research vision. And we took on this very in-depth hardware study. We saw where the numbers were, and that's when we immediately said, well, we got to point a picture of how we get there. So just to give one more viewpoint here, these are all of the contributors to this paper. Yangshan here from the Ames Lab. I obviously can't tell you a lot of their stories, but I do want to highlight, in case you run across them, the sort of organizing team here, which was 3 PIs and 8 junior members like me. Everybody else, you know, sort of really shaped. So like a lot of our hardware advice came from this and this group. Our architects are here. IBM was on the compiler. Yangshan, NASA Ames, and QS BNL, which is thinking about algorithms. It goes on and on and on. And the last thing I want to show is just the fun part of working with particular is that we only involved about half the universities and institutions here. So hopefully we'll be doing more projects like this, sort of taking on this big scale. So with that, I think we're right at time, and time for questions. Any and all are welcome. Thank you.
Thank you, Michael. Questions?
You can ask them like a physicist. You don't have to be a computing architect. I was a physicist to begin with, so. Yeah.
We know where the boundaries, like if you give enough where like like where like if I want to do more, where is the boundary that I can consider multi-node instead of if you put the number of nodes, number of qubits.
No. Let me separate that into 2 questions, one of which I can answer. What would the multi-node system performance be given the single node system performance? And we can exactly put that in. So we now have the simulation tools to build that. Sam Stein from P&L built that. And it's basically that first model I showed with Snoopy and the success regions. As far as exactly what algorithm needs to run there, that depends on the application. And that sort of gets me to the second question, which is should they build it? And that's a financial question, which I don't think I can quite answer. But we can sit down and say, if we want to run this algorithm on a distributed system versus a monolithic system, versus IBM's 433 qubit systems, what would it do if we had a 1200 qubit system with these weak links between them? That's exactly what we can start to talk about. And it probably is, we need about a factor of 10 in each, the internode gate rate and the infidelity to be reduced. That would bring, so from this picture, yeah, that's basically here. So if I come down a factor of 10 in either, then I start to end up in this region, we start to really see the quantum volume exceed that of a single node. And we should expect that to scale to larger systems, not directly for quantum volume, but for other algorithms. Key in that is also, and why Nathan is one of the main leaders here, the distributed quantum phase estimation, which I suspect will be the first real application of distributed quantum computation.
We have a question from Zoom. James, please.
Hey, James.
Yeah. Thank you. Yeah, very nice talk. I recently learned that there are some estimates of problems associated with cosmic ray, say influences or say creating noise from cosmic rays on qubit systems. Is this something you've given thought to as you look at scaling up? What the potential influence of cosmic rays and limiting performance?
Yeah, and in fact, I think it's one of the reasons that some of the companies are interested in this, and one of the ones they don't talk about. In particular, the problem with the cosmic ray is not just that it knocks out a qubit, but it'll screw up all the qubits around it. So your whole chip is in trouble.
Right.
And that's exactly where you kind of like to have your computation distributed across chips. In terms of the particular numbers, that's not something we've gotten into, I think, because we're working with the companies on this. But it is something we're very interested in.
And any thoughts about putting these systems underground to shield from cosmic rays?
Yeah, only wondering why some companies don't seem to have the cosmic ray issues that others don't,
Mhm.
and noticing that they are underground in those cases. Whether a future quantum system needs to be far underground, I think is a fascinating question. I don't have a good answer there. I also know that these systems are highly limited by ionizing radiation. There's a wonderful paper from MIT out on that recently.
Mhm.
Expecting that the best we'll ever get from qubits is about 3 milliseconds, just based on like the concrete, uh, the ionizing radiation from decay in the concrete.
Local sources. Thank you.
So I
Yeah.
think both of those are really interesting questions. I'm sorry I don't have more details on it for you.
Okay. Thanks.
All right. Well, I'll be around.
Let's say we have the two, just set of qubits distributed around distributed on two devices. One in the other in the Then you want to connect these qubits. That is, like you could create, let's say, create the say entanglement between A1 and B1 qubits. So the idea is that is it the entanglement between the A1 and B1 qubits is somehow, let's say, the quantum. How do you manage to make them communicate in quantum way?
So given that the entanglement has been distributed, so given that entanglement, I already have an entangled pair between these two nodes. Is that the question? I'm sorry.
For example, classically, for example, you have a qubit in device A, one qubit A1 in device A, and you have another qubit in device B, and that is called B1 qubit. And then they are in different rooms, and you are in different devices. And you want to create the entanglement between, and how do you use that?
Great. So there's a lot of different proposals for that. The one that we studied in particular is I have A1 and B1, and then I also have A2 and B2 wires. And the wires are connected. So A1 gets entangled with the wire, and B1 gets entangled with the wire. And so basically what that means is there's a photon half in A1 and half in the wire, and half in B1 and half in the wire. And then the photons go out. They're actually going to be converted to optical. This is where we lose 999. But once we do, they can then meet out here in room temperature and interfere. And when that interference happens, you can actually trace it back once it's measured, and we'll end up with an entangled pair between the qubits. That's sort of this picture. I flew through it because it is tricky. There we go. There you are. Yeah. Yeah, so this guy's entangled with this guy, this guy's entangled with this guy. I can then measure these two, and once I'm done there, this guy's entangled with that guy. In some sense, you'll hear this term called entanglement swapping. So if you have a really big network, then you need to do a lot of these entangled pairs because you can only distribute entangled pair. Depends on who you ask, something like tens of kilometers. So if you want to go New York to London, you need to have a lot of entangled pair generators. You're going to produce two here and two here. You measure the two in the middle, and the two of the ends are entangled. So that same story. These are entangled. These are measured. Those are entangled. And there's like a considerable amount of magic to design these protocols, getting them to work with experimental parameters. There's a lot of fiddling. For these two, yeah. So if you're doing it right, yep, both will click at the same time, or they won't click at all. There's actually a weird quantum interference. So you might expect, and take these two, maybe this photon comes down, and it's only detected at one or the other. But actually, both photons come down and are detected, or neither are. And it's called the Hong-Mandel effect. Sort of because there's a minus sign in one of the amplitudes, so you start to add together possibilities. Yeah, it's tricky. There's actually a fun story about this. So, Youngshin was there, and so Simeon at the big C2QA meeting. There were hundreds of people there, and I had so this is when we started circulating this white paper, sort of structure, and started talking to everybody about it. And we had a poster there after the talk, and I left our number two in charge of the poster while I had to run and deal with things. And he's a high performance computing guy, so phenomenal at doing big simulations. Has never seen a dilution refrigerator in his life. And I come back, and the big experimentalists are all sitting there in front of the poster having an argument with each other about this protocol. And our poor number two is just sweating it out, like sitting there while the experimentalists are sort of saying, no, it should be this protocol. No, it should be that protocol. And in fact, the protocol we were using was wrong. We were fine. It turns out there's a very great PRL that I really liked that was wrong. But through nobody's fault, and it turns out none of the experimentalists who were arguing at the time were right. There was another one that came along and was like, okay, this is actually, given the hardware, given the noise profiles, given all these fiddly, very real world noise and performance profiles, this is the protocol that we should be using. So we actually spent, and Simeon Youngshin told me gave a similar talk maybe 6 weeks ago, 2 months ago now, I guess. It actually took us that long to sort of swap out the protocols. And this is one of those things that I wanted to really emphasize the hardware intercompatibility for this. There are many ways to do this. All of them are sort of magic, and all of them have different trade-offs. All right, sounds like we're good.
Let's thank Michael again.
Yeah. Thanks to everybody on Zoom. I appreciate it.